Hello, this is Advanced Math Set 80 Trigonometric Identities. So we're going to start just with a quick review of the basic trig relationships that we know so far. The relationships between sine and cosecant, the relationships between cosine and secant, and the relationships between tangent and cotangent. So just remember those are inverses of each other. Also, looking down lower, sine of negative theta is equal to negative sine theta. Cosine of negative theta is equal to cosine theta. Tangent negative theta is equal to negative tangent theta. Their inverses share those same signs. Okay, so the first thing we're going to do is we're going to prove a couple of these identities. And we're going to start with the trig identity, which is sine squared theta plus cosine squared theta equals 1. And then we're going to prove that that is true. So we take a basic right triangle with sides A, B, and C. And we take what we know about right triangles, knowing that A squared plus B squared equals C squared. So what we also know about right triangles is that the sine of theta is SOH, meaning opposite over hypotenuse, SOH, so. So sine is opposite over hypotenuse. There's opposite hypotenuse, so it is A over C. Cosine theta in the SO, CA, TOA is CA, C-A-H. So cosine is adjacent over hypotenuse. So cosine is going to be B over C. And then finally, tangent is the TOA part of SO, CA, TOA. OA, opposite over adjacent. So A is opposite, B is adjacent. So the tangent of theta is A over B. Going from there, we're going back to sine squared theta plus cosine squared theta. We just showed that sine theta is A over C, so sine squared theta would be A over C squared. That goes to show cosine theta being B over C. Cosine squared theta would be B over C squared. So from here, A squared over C squared plus B squared over C squared. And then we have a common denominator, so we can say A squared plus B squared over C squared. But we've already assumed at the beginning that A squared plus B squared equals C squared, so we can substitute. And we can say A squared plus B squared is C squared on top, and then we have a C squared on the bottom. And that is equal to 1, which then proves that sine squared theta plus cosine squared theta equals 1. Okay, now we're going to go to part B, proving 1 plus cotangent squared theta is equal to cosecant squared theta. We're going to start with the exact same triangle, and we're going to start with tangent theta. Tangent theta, again, is TOA, opposite over adjacent, which is going to be A over B, opposite over adjacent. Cotangent theta is the inverse of that, so it's going to be B over A. So if we go back up to 1 plus cotangent squared theta, that is 1 plus quantity B over A squared, which is the same thing as 1 plus B squared over A squared. So we're going to get a common denominator. We're turning 1 into A squared over A squared, and then we'll put the plus B squared over A squared. We now have a common denominator, so we can rewrite it as A squared plus B squared all over A squared. We already know A squared plus B squared is equal to C squared. So C squared over A squared. And then that is the same thing as C over A squared. If we go back to our right triangle, we can see that we are looking at the hypotenuse and we are looking at opposite. And so hypotenuse and opposite, that's OH, so, but it's inverted, so it's going to be the inverse of sine, which is cosecant. Cosecant squared theta, because C over A is squared. And that has proven that identity. Okay, and then finally we're going to prove part C. Part C, we go back to the original triangle, ABC. We start with tangent squared theta plus 1. Tangent, again, is opposite over adjacent, which is b over a, and we're squaring it. We're adding 1. We want to get a common denominator, b squared over a squared plus a squared over a squared. That is equal to b squared plus a squared all over a squared. I already know a squared plus b squared is equal to c squared, so we have c squared over a squared. This is the same thing as c over a, quantity squared. And then going back to your triangle, c over a is going to be hypotenuse over adjacent. That's AH. It's the inverse of cosine. The inverse of cosine is secant squared theta. That proves that identity. Okay, and then for each of these identities, there are 3 ways to write them. So first of all, sine squared theta plus cosine squared theta equals 1. If we divide everything by sine squared theta, we end up with 1 plus cotangent squared theta equals cosecant squared theta, which is b. To get c, we are going to take sine squared theta plus cosine squared theta equals 1, and instead of dividing by sine squared theta, we're going to divide everything by cosine squared theta. Dividing by cosine squared theta gives us tangent squared theta plus 1 equals secant squared theta, which is our third identity. Now, we can also write identity A as, if we solve for sine squared theta, it is 1 minus cosine squared theta. We can also write it as cosine squared theta equals 1 minus sine squared theta. Going to B, we can solve for 1 and say that 1 is equal to cosecant squared theta minus cotangent squared theta. Or if we solve for cotangent squared theta, we can say that is equal to cosecant squared theta minus 1. Okay, and then finally part C, if we solve for tangent squared theta, we have secant squared theta minus 1. And if we solve for 1, we have secant squared theta minus tangent squared theta. Sine squared theta plus cosine squared theta is kind of like the one that is the base. It's the beginning of everything. So if you can memorize sine squared theta plus cosine squared theta equals 1, you can basically derive everything else from that, as we've seen from these last 2 slides. So sine squared theta plus cosine squared theta equals 1. If we divide by sine squared theta, we end up with 1 plus cotangent squared theta equals cosecant squared theta, which is identity 2. Sine squared theta plus cosine squared theta, if we divide everything by cosine squared theta, you get tangent squared theta plus 1 equals secant squared theta. I think we already showed that. Okay, so now we're to the problems. So these problems really are like solving a puzzle. And sometimes you go in the right direction. Sometimes it's like a maze where you hit a dead end and you have to go back and then try another way. But what you try to do is look for patterns. You always leave the right side alone and you work and figure out how you can manipulate the left side to look like the right side. It's kind of like solving a Rubik's Cube. You know what you want the end to look like, so you just make moves to figure out how to manipulate the left. So with this one, what we're going to do is try and make it look like sine squared x. So going back to our identities, we look to see what we have. I can see that I have a 1 plus cotangent theta, and that is equal to cosecant theta, and cosecant theta is very close to sine theta. So I am going to use that one. Actually, I'm going to use it in a minute. First of all, we've got tangent squared theta and secant squared theta up in the numerator, and then in the denominator, we've got 1 plus cotangent squared theta. So we're going to use both of those. If I solve tangent squared theta plus 1 equals secant squared theta, if I solve that for 1, I get secant squared theta minus tangent squared theta. There's your numerator. Your numerator is already solved for 1. So I can replace the numerator with 1. And then, like I already said, I have 1 plus cotangent squared x on the denominator. But looking over here, the orange highlighted 1 plus cotangent squared equals cosecant squared. I can just substitute cosecant squared. Now, cosecant squared is the inverse of sine squared, so I have sine squared x, which matches what I wanted. Okay, the next problem, show that 1 over tangent A plus tangent A is equal to secant A cosecant A. So with this one, you may be tempted to square things, but the smarter or the easier way to do it is to just rewrite tangent in terms of sine and cosine. So we're going to write it as 1 over sine over cosine, and then plus sine over cosine. This way we can flip the first term and say that it is cosine A over sine A plus sine A over cosine A. Now we can get a common denominator, and we can multiply the right by sine A, the left by cosine A. So we end up with cosine squared A plus sine squared A on the top, and then cosine A sine A on the bottom. We already know that cosine squared A plus sine squared A is 1, and then we can just leave cosine A sine A on the bottom. But we have now inverse properties. 1 over cosine A is secant, 1 over sine is cosecant, and that is what we were looking for. We now match what we started with. Okay, next problem is 1 over 1 plus cosine A plus 1 over 1 minus cosine A equals 2 cosecant A. So we've got cosines turning into cosecants. So we have to figure out what on earth can we do. I do have a fraction, so I'm probably going to want to get a common denominator at some point. So I think that's where we'll start. So we will start with 1 over 1 plus cosine A. We'll multiply it by 1 minus cosine A over 1 minus cosine A. And then the second side, we'll just do the same thing, but 1 plus cosine A over 1 plus cosine A. Working this out, we get 1 minus cosine A on the top, plus 1 plus cosine A on the top still, and then we have a common denominator of 1 minus cosine squared A. Now, I know that sine squared x plus cosine squared x equals 1, and I know that 1 minus cosine squared x is the same as sine squared x. So 1 minus cosine squared A is going to be the same as sine squared A. On the top, 1 plus 1 equals 2, minus cosine A plus cosine A goes away. So I end up with 2 over sine squared A. The last step that I need to do is turn that into cosecant instead of sine, and I have the right answer. Finally, show cosine A over 1 plus sine A plus 1 plus sine A over cosine A is equal to 2 secant A. So in this case, I also have a situation of wanting to get a common denominator. I can't really do anything until I have a common denominator, so I'm going to multiply the left by cosine A over cosine A and the right by 1 plus sine A over 1 plus sine A. So that gives me cosine squared A, and then on the right, because it is two binomials multiplied by each other, I'm going to end up with 3 terms. I'm going to end up with 1 plus 2 sine A plus sine squared A. And then on the bottom, I just have the common denominator of cosine A times 1 plus sine A. Now I can do some combining because I have a cosine squared A and a sine squared A, and I know that when they come together, that makes a 1. So those go away and turn into a 1. So 1 plus 1 is 2, and then I have 2 sine A left over. So 2 plus 2 sine A, and then on the bottom I have cosine A times 1 plus sine A. So I have a sine A on top and a sine A on bottom, but I need to get rid of those 2's. I've got to factor the 2 out. So factoring the 2 out enables me to do some canceling. 2 times 1 plus sine A over cosine A times 1 plus sine A. I can cancel out 1 plus sine A to get 2 over cosine A. 2 over cosine A is the same as 2 secant A. And that is what we started with.